The last speaker of the second morning session is Peter Klimek. Peter is professor at the Medical University of Vienna and faculty member of the Hub. His research explores the possibilities that big data and complexity science offer for the future of medicine. His interests also include complexity economics and socioeconomic modeling, as well as techniques for socioeconomic impact analysis of new technologies. Welcome.
So, thank you. So I'm already standing between your lunch and so I try to keep this short. I've only prepared 3 slides and none of them talk about any of the work that we've been doing. We were asked to talk about complexity science. Where do we go from here? And I will try to answer this question the only way that I can do, namely by being fully subjective. I joined Stefan's group 10 years ago, almost exactly 10 years ago. And at this point, we were at the Medical University of Vienna doing some, what you would now call basic network stuff, and nobody there at this university in the statistics department, the computer science department there, basically had an idea of what we were doing there and for what this was good, what we were doing. Now, last year there was a symposium from our department, and there were 5 talks, and 4 of these had in some way a network in them, and we're talking about networks. What I'm saying here is that most of the things that we have been doing in the last couple of decades in complex system science are becoming old and boring and are becoming more or less standard. We're not doing anything new anymore. So that this network analysis, for example, is now a standard data analysis tool, like a regression model, like an information theory, and so on. So this is one point that I want to stress here, that we somehow need to think about where do we go from here. We need to be aware of, if we keep doing like we did it now, we're basically just iterating incrementally on ideas that were cool in the 90s. The other thing, many of us here have said that multidisciplinarity, interdisciplinarity is important here. Well, how do we respond to the challenge? Basically, we invent a new discipline. We have now journals devoted to complexity science. I mean, how absurd is that? That we try to combine disciplines by making a new one, by inventing our new set of tools, and say, in order to be able to follow this discipline, you need to know what a multi-layer network is, what a power law distribution is, and so on. I mean, from one point of view, it's absurd. So what I want to say here is that we somehow need to step out of our narrow boundaries of complexity science and need to look outside to get some inspiration on where to go. And there I first want to look backwards. Soon after, I don't know if any of you has so far figured out which kind of computers these are. Soon after Keynes published his groundbreaking work on macroeconomics, people figured out that his model essentially describes a fluid. So money is like a fluid, and markets are like a plumbing system that puts the money around different places of the economy. So already in 1893, the first macroeconomic simulator was computed, which was a hydraulic system. In 1949, Phillips constructed the so-called MONIAC. Phillips, by the way, is the guy who discovered the Phillips curve, the famous relation that unemployment is negatively correlated with the inflation rate. And this is how he did his experiments in Cambridge, basically building a plumbing system. I argue that this has all the ingredients that we would now call complexity science, even being more than 100 years old. Obviously, it's a network model. You see the plumbing systems here. More importantly, people have figured out that there is a connection between an economic theory and a physical process, namely this is hydrodynamics. And they use this to make a computer for this kind of systems. So what happened to economists? They were cool once again, and now they're basically doing the same stuff on computers. So to get some other inspiration, where I think people who thought the way of how to understand real systems in detail, who thought this through, and now basically I can only reiterate what Max said before. We should look at engineering. If you talk to people that are in engineering, who are in industrial production systems, who try to understand complex systems within these boundaries, what is all the rage here are so-called digital twins. So the idea is you have a complex production facility. you want to manage this, you want to know how the system operates. So what you do is, with all the advances that we have in sensor technology, with all the advances that we have in data processing capacity, we build a digital twin. And if we want to make some kind of interventions, if we want to optimize the system, if we want to learn out what's going on, we can study this in the digital twin of the original system. And by the way, this is also not new. If you think about NASA, what they do is, to the spacecraft that is in orbit, they build a real physical twin, and for any kind of intervention, they test this here. And as Max has said in a much more eloquent way, and I can do this, this goes a long way towards understanding the system. So what does this mean for us as complexity scientists? Of course, you see where I'm going with that. At the end of the day, what we're looking at are complex socio-economic, technical, molecular, biological systems. And the only way that we can handle these technologies, and from learning at how other people understand this kind of systems, is by trying to understand these systems, by building models of them, by building digital twins of them. And I think this is more or less where we can contribute most to the scientific endeavor in general, and where we can make a real impact. I mean, at the end of the day, most of us are still crowdfunded and should somehow repay this to the population by doing something meaningful. And this is where I think we as complexity scientists, this is something that we should, a direction in which we should more or less move. So to conclude this, of course, this is only possible by working multidisciplinary, but here I don't mean in the way that maybe many other people implied this or sometimes use this. I think in order to be fully multidisciplinary, we need to keep the cooperation within our minds. This is the only way that we can build such complex models. We need to become experts in the systems that we're modeling. If we're working about genetic models, yeah, we have to learn this biology. If we learn about social systems, we have to learn the theory there. I don't see any other way of how we can proceed without building our new parallel community and without basically just doing scientific masturbation. And with this nice picture, I wish you a nice lunch.